I'm a PhD student in CISA in Trieste, and thank you for the invitation. About my project, which consists of a stacking analysis in the UV plane on a sample of strongly lensed acid-forming galaxy at high redshift that we observed with ALMA telescope. And I'm a first-year PhD student. These are really the first step of my project, but I think the idea on the base are really promising, and I want to share with all of you the aim of my project. Which are the targets of our research in our group? Marika already talked about yesterday, and they are the high redshift acid-forming galaxy, which are a really promising object to study because they have a relevant role, for example, in the cosmic star formation rate density. They contribute to the density almost at 30% at redshift 2, for example. And also they are very important to test some particular coevolutionary model when we find the black hole accretion follow the star formation rate of a galaxy. The problem is that these objects are compact and so difficult to resolve. So we can recur to the strong lensing technique. So we can increase the luminosity by a factor and also stretch the size of the galaxy. So we are able to resolve spatially. Another problem is that they are very rare events. So we need a very wide survey. In particular, we can use the submillimetric band, which are very effective in finding the lensed acid-forming galaxy. And we will see why. First, different models predict that there is a drop in the number counts of unlensed acid-forming galaxy with the flux luminosity over 100 microjansky in this band. And also, we have the intrinsic advantages of observing in the submillimeter. For example, the negative K correction, which in our case, there's a positive effect because in this band, the luminosity very high in the infrared perfectly balanced the effect of the redshift. So we resolve this problem. Also, these galaxies in this band are not affected by dusk obscuration, and there are no contamination for the foreground lens. So we are able to spatially resolve this service in this band. So really promising. It's interesting why what submillimetric survey perform our analysis. The best candidate, of course, is the Herschel lateral survey, which is the widest area extragalactic service, where Negrello, in his work of 2017, find 80 candidates strongly lensed galaxy, where we can see have a very high luminous in the infrared band and the space across a very wide range of redshift, reaching also redshift of 4.5. In this catalog, 22 strong lensing events are confirmed to date, but there are also different observations of the same sources in with other telescopes. For example, we want to find some possible matches with the short survey that we talked about to you yesterday, and Miriam will talk about in this talk tomorrow. From these 80 candidates strongly lensed, we found 50 targets found in the ALMA archive. So my project, is to perform a stacking analysis on this sample of galaxies. Just to give a flavor of what is spectral line stacking analysis. It consists in combining multiple images together to improve the signal noise ratio in order to obtain the line, reduce the noise, and so detect the spectral line in a galaxy, also in fainter galaxy. In our case, since we are studying the acid-forming galaxy, we are interested in dust tracking lines in the stellar medium, for example, the well-known C2, the O3, or the CO line. But we are also looking to find more complex molecules that can give us an idea of the physical condition in the stellar medium, for example, transition of the water on other complex molecule spectral line. This technique is usually done in the image plane. For example, we can see the work of Spielberg to 2018, which consists of a stacking of 22 sources with a wide range of redshift to obtain the average extreme spectrum of this acid-forming galaxy. The advantages is that, as I said, is a well-known technique in literature. And also we can use directly the image on the ALMA archive to perform this analysis. The problem of stacking the image plane is that we need the data we want to stack need to be on the same angular scale, or they must have a known distribution of emission as a function of the angular scale. In addition, when we go to high redshift, we are increasing the bandwidth with the redshift. So there are effects that are not negligible anymore. We need to take in account. So we can try to stack in the UV plane, but what are the pros and cons of this technique? The pros is that we have no more the problem of the angular scale or the bandwidth increasing when we work in the UV plane. And also we have a second advantage because simply drawing the visibility data of different galaxies can allow us to better cover the UV plane. In this way, we can remove the whole interpolation problem that we have when we pass to the UV plane, to the image plane due to the Fourier transform. Of course, there are some disadvantages, which are this project is computationally very expensive because we were working with the raw data, not just the image. And also, this analysis has been done in literature since now, just with a sample of local galaxies or galaxies that are the same spectroscopic redshift. The aim of my project, my objective, is to try to reframe the visibility data. In this way, we were able to perform this analysis with galaxies with different redshift, also very high redshift, from this different observation projects. So we can use different data from the ALMA archive to different observation. And also with different angular resolution, because we have no problem, we have no more the problem with the angular resolution. So my project will consist of writing a new CASA-based code, which will be able to perform stacking the UV plane and try to use this code of our sample Daciforme galaxy strongly lensed. So we need to be careful because what we need to do, our intent is to modify the visibility data in order to obtain, after we clean the EMS, we want to obtain the same image we would obtain simply reframing the image that we have obtained with the observed data. So we need to multiply per 1 plus z all the quantity that are linked to the frequency. So the bandwidth, the resolution, and everything. But we need to preserve the angular scale. So we need, for example, to divide the point in the UV view, the UV plane, and also the baseline by the same factor to preserve the angular scale. And here I will show an example on the galaxy that Marika talked to you about yesterday, and also the subject of her paper. In this galaxy, we perform the restraint of the visibility. We can see the UV plane. This is the UV plane observed, and this is UV plane restraint. As we can see, the pattern is pretty identical. What is changing is simply the range of the axis. And the same thing is for the antenna position, because if you want to modify the baseline, we need to modify all the antenna position. And we were saying we are simply modifying the axis. So we achieve our result, because this is the image obtained with the observed visibility. So the classic cleaning with ALMA. So in fact, we can see here the observed visibility, because we are looking in band 6, I think, yeah, band 6, and this is the observed frequency. And this is the image we obtain by reframing the visibility, which is identical, as we can see here. I don't know if you can see, I can see the band of zoom, but I think you can see. And they are the pretty same value for the flux. The only thing is changing is the frequency. So if we take the image on the left, which is the one that it's classically produced with the raw data, and we reframe with CASA, we would obtain the same image performed with the visibility reframe, which is what we want to achieve. Of course, this process and some caveats in it, it can be very tricky, because, for example, just to reframe the frequency, we have no CASA task or tool that can allow us to do that. So we need to manage manually all the raw data and modify it just by hand. So that can give some possible coherence problem, because we need to find all the quantities can be frequency dependent, wavelength dependent, can be stored in the table of the EMS file that we can find. Also, since we are working with the raw data, this technique is really computationally heavier and slower than stacking the image plane. So we need to find some high performance technique. We need to parallelize the code in order to obtain an acceptable and fast result. And also, which can be an advantage and disadvantages, there are no similar coding now in literature that does that. So we don't have like a reference to match our result. So we are trying, we are making different tentatives, we are seeing step by step what is working and what is not, to understand also CASA more and understand how can we achieve our result. So just to give Anna the conclusion and the future perspective of my work, as I said, they are just the first step. I'm hoping to very soon able to perform the stacking on our sample of Galaxy. So the objective of my work is to perform stacking on this wider, stronger lens narcissistic-forming galaxy to obtain some spectral lines that can allow us to study interstellar medium. For COPS, for example, there are the waterline analysis performed by Perotta that the article is just being submitted to APJ, and we want to try to find the waterline in this sample of this sister-forming galaxy and to link the two works together. And since the data doesn't have to be from the same project anymore, we can now find a new target in ALMA, new survey, we can open new proposal, we can just looking for the very different wide range of galaxy. And with some adjustment, since we are working with the raw data, but we are simply modifying visibility, baselines, antenna position, which are pretty classic data in each form or in each format for different telescope, we were hoping to expand this code for also different telescope format file. For example, we want to try with SHORE's survey that Marian will talk about tomorrow, and so extend this code to not only to ALMA, but to all the possible radio interferometric data. So this is all, and thank you everyone, and I